So welcome everyone. It's time to start this afternoon session. Our first speaker is Professor Sunitha Varadarajan, who I just learned is actually a student of our convener, conference organizer, T.R. Govindarajan. So she has a PhD from Madras University, but for work done here in Mat Science. Was it still called Mat Science or was it already IMSC? It was Institute for Mathematical Sciences. But it's always, I think of it as math science. So Professor Varadarajan's research is in a number of areas. She does work in quantum gravity, ADS, CFT correspondence, and also aspects of string theory or string framework, was it? Yeah, string framework. So Sunitha will tell us on this very interesting topic, quantum stability of black holes.
Thank you very much for that introduction. I'd like to describe myself as a mathematical physicist. That covers just about everything without having to be part of a group and try to defend the group. So what I'm going to be speaking about today is a notion of quantum stability of black holes, and I will actually do a calculation. And I want to apologize in advance to all the students that this is going to be a very technical talk, and it's technical for a reason. So when I was asked to speak at this conference, I wanted to speak on some work of mine which has benefited at least indirectly from something Chandrasekhar has done. And what I will try to show in this talk is that the quantum stability computation that I'm doing relies very heavily on techniques used by people working on classical stability of black holes, including Chandrasekhar. So the idea is to highlight the techniques, and so it's a technical talk. So I apologize in advance for that. So let me see if Okay, so let's first remind ourselves what we mean by the classical stability of a black hole, like the Schwarzschild black hole. So lots of people have worked on this area, like Ricci, Wheeler, Price, etc. But a wonderful account of the classical stability of the Schwarzschild black hole is found in Chandrasekhar's book. So the idea is very simple. You have this Schwarzschild black hole and you perturb it slightly. And your perturbation is something very localized. And you want to know what happens to the perturbation as over time. Does the perturbation grow or does it remain small? Does it remain bounded? So technically the question is, if at some initial time I perturb the Schwarzschild black hole by a perturbation of compact support, then will this perturbation remain bounded at all times as it evolves? So I can take the Schwarzschild metric and I can add a small perturbation. The smallness is measured by this epsilon, this parameter epsilon, which is epsilon is positive, and this is my perturbed metric. So what I want is that I know that this Schwarzschild black hole satisfies the Einstein equation, the vacuum Einstein equation, which is that its Ricci curvature is 0. Okay, so I want my perturbed spacetime to also satisfy Ricci curvature of the perturbed spacetime equals 0, and borrowing language from quantum field theory, I will call this an on-shell perturbation. So in the approximation that this epsilon is small, I can neglect terms order epsilon square and higher. This is a very common technique in perturbation theory. I keep only terms linear in epsilon, and then I look at this equation R mu nu of the perturbed spacetime equals 0 in that approximation. So what all these people showed, and what is clearly shown in Chandrasekhar's book, is that this equation reduces to a second order linear ordinary differential equation which you can solve, and what all these people found is that there are no perturbations that actually grow in time. So a Schwarzschild black hole is classically stable, and this was generalized to the higher dimensional analogs of Schwarzschild black holes by all these people. So this is all this is the idea of classical stability, and lots of techniques were introduced to actually do this classical stability problem, and we will find these things useful in the talk. Okay. So what I want to concentrate in the talk is on a notion of quantum stability of a black hole. Now, as you have heard in all the talks before, we don't really have a theory of quantum gravity. So what do I mean by quantum stability of a black hole? So quantum stability means stability of the black hole in quantum gravity, but we don't really have a theory of quantum gravity. But that did not prevent people from trying, and that did not prevent people from trying to do what you do with other fields in gravity. So when you have a field, normally when you have fields and you quantize them, so you have quantum field theory, you have some techniques developed in quantum field theory. One of those techniques is the path integral approach, and people try to do the same thing to quantum gravity. So in the path integral approach, the starting point is something called the partition function, which we have already seen in several talks. So the partition function in this quantum gravity is an integral over all possible metrics modulo some coordinate transformation freedoms or modulo diffeomorphisms. And these metrics are weighted by a measure. And the measure is exponential of minus the Einstein action. So this object is the partition function. And to make connection with the Einstein equation is just obtained by taking the first variation of this Einstein action and setting it equal to 0. So there are some special geometries that solve the Einstein equation. I call them classical geometries or classical metrics, G-classicals. Okay. But those are not the only geometries you integrate over in this partition function. So each geometry comes with this weight, exponential of minus s. So now let's take one particular classical geometry. So the Schwarzschild metric is a classical geometry. The higher dimensional analogs of Schwarzschild are also, the Schwarzschild Tangalini spacetimes are also classical geometries. So I forgot to mention here that these metrics, you need to do a procedure to these metrics. You need to rotate time to imaginary time, and these are so-called Euclidean metrics. Okay, so let me start with one particular classical metric. It could be the Schwarzschild metric. And I'm going to perturb the Schwarzschild metric just like in the classical stability calculation. So I have a perturbed metric which is G classical plus epsilon h, where h is a perturbation, epsilon is small. I can put some appropriate boundary conditions or asymptotic conditions on the metric. Now the question, in quantum stability, the question that's of interest is this. Does this perturbation actually decrease the Einstein action? So suppose I perturb this classical metric and it ends up decreasing the Einstein action, then what happens? Well, what happens is that this new perturbed metric has a higher weight in the partition function than the original one. Okay. So then we would conclude that that classical geometry that we perturbed was actually unstable under this perturbation. So this is a notion of quantum stability. Of course, we don't have a quantum theory of gravity, but at least in some semi-classical approximation, this is a notion of quantum stability of that classical geometry. So one of the very old results is due to Gross, who gave a talk yesterday, and Perry and Yaffe. And Gross, Perry, and Yaffe actually found out that the Schwarzschild metric has an unstable mode. Okay. The paper is a little bit ambiguous about all the other possible unstable modes, so the question remains whether there are any other unstable modes, whether we can obtain a better understanding of what this instability is. So just a technical detail here, the perturbed metric in this Gross-Perry-Yaffe calculation approaches R3 times this circle. Yeah, it's a Euclidean time. So this mode is evidence of this quantum instability of the Schwarzschild black hole, at least in the semi-classical picture. And this quantum instability actually has connections to another famous instability for those of you who are familiar with it. It was shown by Real that this quantum instability is exactly the same as the classical Gregory-Laflamme instability of a black p-brane. So a black p-brane is nothing but a Schwarzschild metric in 4 dimensions plus a flat metric in p dimensions. Okay. And these people, and Real showed that this is precisely the same as the Gregory-Laflamme instability. Okay, so that was one notion of quantum stability. And now there is a related notion of quantum stability, and this comes from string theory. So I'm going to first state what the conjecture is, which gives you this notion of quantum stability, but I will try to also say it in words for the students. So the conjecture so this notion relies on the conjecture that many quantum processes or optional processes in string field theory are approximated by renormalization group flows. So the next 2 slides are going to be very technical because I'll try to explain what this conjecture actually is. But let me say it in words for the students. So in yesterday's talk on string theory, you had this picture of a geometry in which a string is propagating. So what this conjecture is trying to tell you is that the propagating string affects the geometry. A question you might ask is, how does it change the geometry? And this conjecture says that the way it changes the geometry is through the solutions of a differential equation, which is actually called this renormalization group flow. Okay. So I'm going to show you in the next couple of slides what that differential equation is and a little more about the conjecture, but that's technical. Okay, so let's come to what renormalization group flows in string theory are. So I have a geometry in which a string is propagating. This geometry is called the target space. It's got a metric G on it. And as the string propagates in this geometry, it traces out a two-dimensional sheet called the world sheet. And I have some coordinates that tell me how the sheet is embedded in this bigger space, and those coordinates are x. And in a certain approximation, the dynamics of how the string propagates in this target space is given by an action. It's given by a quantum field theory which lives entirely on this sheet. Okay, so it's a two-dimensional quantum field theory. And the quantum field theory looks like this. Forget about the details. Just note that the quantum fields are actually the embedding coordinates of the sheet in the bigger space. Okay, these are the quantum fields because these are the only dynamical things in this problem. And the metric of this bigger space, which is the target space, actually appears in this quantum field theory as a coupling constant. So from our knowledge of quantum field theory tells us that when we do a renormalization group transformation, coupling constants flow. So the metric actually flows under the renormalization group transformation, and the flow of the metric is a partial differential equation that looks like this. So on the left hand side you have the flow of the metric with respect to this parameter tau. Okay. On the right hand side you have the intrinsic curvature of the target space itself. So this is an equation where the geometry is changing and the change is driven by the intrinsic curvature. Okay. So alpha prime is a constant that appears in string theory. I don't want to spend too much time about it. It's small. You can think of it as order of square of the Planck length, which was introduced before. And so I can neglect order alpha prime square terms and higher. Okay. And one is not interested just in the flow of these metrics. One is interested in a flow of metrics modulo diffeomorphisms, and a local version of diffeomorphism is just a coordinate transformation on a spacetime. Oops. So neglecting order alpha prime square terms and higher, this flow, this partial differential equation also appears in mathematics where it's called the Ricci flow, and it was in the news recently, I mean a few years ago, because it was used to prove the Poincare conjecture. So another thing I want to say is that the fixed points of this flow, so the fixed points are given by dg by d tau equals 0, actually satisfy Ricci tensor equals 0. So this is precisely the Einstein equation, and the solutions are the classical or on-shell geometries. And in this case, this sigma model, this quantum field theory, is actually a conformal field theory. Okay, so let me come to this conjecture in string theory, which is so vital for this notion of quantum stability. So the conjecture in string theory, which is due to many people, is that many off-shell processes in string field theory, or many quantum processes in string field theory, which are mediated by tachyonic operators, are actually approximated by solutions to that partial differential equation. So this is a very non-trivial idea, because what it's doing is it's identifying dynamical time in the string field theory with the RG flow parameter. Okay. So if you believe that conjecture, then it should imply that stability or instability of a classical geometry under the RG flow is indicative of its quantum instability. And the argument for this, for this idea is actually that in many cases, your on-shell geometry is described by a conformal field theory. In many cases, it's possible to construct operators in this conformal field theory which are relevant perturbations, and they cause RG flows, and they're also tachyonic, thereby triggering these quantum processes. So this is what leads to the idea that somehow quantum instability is related to instability under RG flows. Okay, so those were the two technical slides. So what we propose to do in this talk is we propose to investigate the quantum stability of Schwarzschild black holes and its higher dimensional analog by studying the stability of the black hole under that particular partial differential equation, which is the string theory RG flow or the Ricci flow. Of course, I'm going to show that this problem is very closely related to the quantum stability idea in the path integral approach. In fact, they're almost the same. Okay, so whatever computation I do for one also holds for the other. And the advantage is that mathematically what you're doing is you're trying to see if a fixed point of a flow equation is stable under the flow. This is mathematically very well posed for this particular flow. And what I want to highlight in the rest of the talk is all the time in trying to solve this problem, you're going to borrow techniques from the classical stability analysis of Chandrasekhar and others, and this turns out to be very useful. So let's come to the details. Okay, so this is work which was done in collaboration with Suvankar Datta, who was a postdoc. So let's start from first writing down the spacetimes whose stability we want to investigate. So these are the Schwarzschild and its higher dimensional analogs. So most of you might have looked at the metric of the Schwarzschild black hole. So you have a metric which looks like this. For the higher dimensional analogs, of course, you also have a d-dimensional sphere here instead of a two-dimensional sphere, and the function f of r is different. So this d-dimensional sphere that appears here will play a role in all our future computations, so I just want to highlight it. Okay. So these metrics actually obey the vacuum Einstein equation, so the Ricci tensor is 0. So we are interested in the stability of these metrics under this particular partial differential equation, which I will refer to it as Ricci flow from now on. So the flow of the metric is driven by the intrinsic curvature. So this metric is actually a fixed point of this flow because Rij equals 0 for that metric. Okay, so now I have this metric which I call G Schwarzschild Tangolini, GST, and I perturb it slightly by a perturbation. So I have this perturbed metric, and the question that I am now interested in asking is, does this perturbation remain bounded for all tau? So I start with this perturbed metric. This is my initial condition for this partial differential equation, and I flow this, and I want to know what happens for tau, for all tau. Okay. So if the perturbation remains bounded, remains small for all tau, then I would say that the Schwarzschild Tangolini metric is actually stable under this flow. And I'm going to do this in an approximation where epsilon is small, so I can neglect terms order epsilon square or higher. So that's a linearized approximation, and so this would be a result on linear stability. So that's mathematically the problem. But even before we start, we need to ask which type of perturbations should we consider. Okay. So why should we worry about, why can't we just take arbitrary perturbations? Well, the reason is that that partial differential equation, Ricci flow, does not make sense. It's not a well-posed partial differential equation when you consider it as a flow through all Lorentzian spacetimes. Okay, so it doesn't make sense at all. It's like a backward heat equation. It's like a heat equation with the wrong sign. This equation actually makes sense as a flow through static spacetimes. So these are the spacetimes which can actually be Wick rotated. Okay, and in fact, although this is never clearly stated, it's assumed in the derivation of the Ricci flow as an renormalization group flow in string theory. Okay. So we can only consider static perturbations because otherwise that differential equation doesn't make sense. Okay. So we consider static perturbations of the Schwarzschild and its high dimensional analogs. So now I want to do this perturbation problem, and what is the first question that we ask whenever we want to do such a problem so this is something which we ask in many problems like this in physics. Is there a gauge freedom in this problem? Okay. So it turns out that there is a gauge freedom. So there is this diffeomorphism freedom. So if you do diffeomorphisms, the Ricci flow is not invariant under diffeomorphisms. It does not retain its form. Okay. But if you do diffeomorphisms which are generated by a vector field V, then your Ricci flow actually gets modified to this particular flow. So what I can do is I can look at this particular flow instead, which is just related by a change of coordinates to the original flow, and I can choose my V appropriately so that my computation becomes simple. So let's go back up there. We have a perturbed metric. Perturbed metric is G Schwarzschild plus epsilon h. Okay. And I already said that my perturbation has to be static. So h has to be a function of the radial coordinate, the angular coordinates on the sphere, and the flow parameter tau. Okay. So I also work in a linearized approximation where the perturbation is small, and then I can use the gauge freedom which I described in the previous slide. So I get a very nice equation for the flow of h. The flow of h is just given modulo some constants by this operator delta L acting on h. Okay. What is delta L? Delta L is just the Laplacian plus some curvature terms. It's called the Lichnerovich Laplacian. And the curvature tensors here are all the curvature tensors of the background Schwarzschild metric. Okay. So that's the Lichnerovich Laplacian. Now I just want to tell you that the problem of stability under this flow, so the problem of finding out what happens to the perturbation under this flow is very similar to the problem of stability in the path integral approach to quantum gravity. And the connection is as follows. Take this perturbation and just separate out the dependence on r and the angular coordinates from the dependence on the flow parameter tau. So you assume an ansatz where the dependence on the flow parameter tau is of the form exponential omega tau. Okay. Then clearly if omega is bigger than 0, this perturbation is growing. Okay. So the perturbation is unstable. But if omega, so when you put in this ansatz back into that equation, what you get is an eigenvalue equation for the operator delta L, which is the Lichnerovich Laplacian. So unstable perturbations mean omega is bigger than 0, and it also means negative eigenvalues of the Lichnerovich Laplacian. And this is precisely the instability of Gross-Perry and Yaffe. Okay, so if I assume a special ansatz, then the two problems are actually the same. We are looking at Riemannian metrics now. So I already said that the Ricci Flow equation does not make sense on arbitrary Lorentzian spacetimes. So we are only looking at static spacetime, the flow on static spacetime. So we can then Wick rotate. Yeah, is there a question? I'm sorry? No, I'm not assuming anything for Hij at the moment. Okay, let's see if I can. Yes. Okay, P is just some arbitrary function here. Okay, P is, oh, I'm sorry, it's a tensor. I forgot to put the indices. It's some arbitrary tensor. I'm just separating out the tau dependence. Okay, so the question that we are asking is that Schwarzschild Tangolini metric, is that Schwarzschild metric stable under this particular flow? So we want to know what happens to the perturbation under this flow, where you have this Laplacian plus curvature terms, and the Laplacian and curvature terms are all taken on this background Schwarzschild metric. So again, our strategy is borrowed from classical stability analysis and relativity. And how do we normally do that? Normally we break up a perturbation into several pieces, and we do this for a reason which we'll come to later. So how do I want to break the perturbation? I want to break it up into a transverse traceless piece. So transverse means that del I Hij is 0. Traceless means Gij Hij is 0, where Gij is the background Schwarzschild metric. Okay. So I break it up into a piece which is transverse traceless, break it up into a piece which is pure trace, and a piece which is called pure divergence. Okay. So this breakup is very standard in classical stability analysis. And the reason I do that is because analogous to the classical stability computation, pure divergence perturbations, so those perturbations where these two pieces are not there, we have only del I Yj plus del J Yi, these types of perturbations are actually gauge. Okay. But unlike the classical stability computation, the trace of the perturbation here is not gauge. Okay, so I now broke up this perturbation into these three special pieces, and I have this flow equation. Okay. So obviously I need to consider the flows of each of these separate pieces. Okay, so, and they could all be in principle coupled to each other. So it could be a mess. So let me do the simplest thing first, which is the flow of the trace. Okay. So if I just have the trace, I just simply trace out my previous flow equation and I get this. So the flow of the trace is really simple. dH by d tau is just the Laplacian of h. dh by d tau is just Laplacian of h modulo some constants. Okay, so I have this problem and I have my background Schwarzschild metric. So it's very obvious what kind of ansatz I should choose. My trace depends on the radial coordinates, spherical coordinates and tau. So I have some radial dependence, I have some tau dependence which is of this form exponential omega times tau, which tells me whether there is a growing mode or not. And I have my angular dependence which is very naturally given in terms of the spherical harmonics. Okay, so h tilde just satisfies Laplacian on the sphere times h tilde equals lambda t tilde h tilde. So clearly if my omega t is positive, okay, then this whole solution is growing in tau, so it's an unstable mode provided the solution is normalizable, provided h is normalizable. Okay. So solutions with omega t bigger than 0 which are normalizable are what we are looking for. Those are the unstable modes. And we can plug this guess back into this equation and it's very easy to figure out that there are no unstable modes if and only if the eigenvalue on the sphere, eigenvalue of the Laplacian on the sphere obeys this inequality. But the eigenvalues or the eigenspectrum of the Laplacian on the sphere is known and it always obeys these inequalities. With our conventions it's actually negative. So what it's telling you is that there are no unstable modes if this inequality is satisfied and it's always satisfied, so there is no instability in the flow of the trace. Okay. And there were some boundary conditions we assumed here. We could assume Dirichlet or Neumann boundary conditions on the horizon, or as r goes to infinity it doesn't matter. Okay, so we had actually split up our perturbation into 3 pieces, one of which was the trace piece. We still have to worry about the other pieces. Yeah, you can assume Dirichlet on one end and on Neumann on the other, it doesn't make a difference. Oh, so this is the Euclidean Schwarzschild metric. So in this differential equation it's natural to treat the horizon as a boundary because it's anyway goes only from the horizon to infinity. No, we remove that, right? We have the time is periodic with the appropriate period. Okay, so now we have to worry about the other piece which is the transverse traceless part of the perturbation. Now, whenever we see the transverse traceless part and we see the operator which is the Lichnerovich Laplacian, which also appears in classical stability analysis, we remember a very nice property of this Laplacian. Okay? The nice property is that when your background metric in which you compute the Laplacian, when that background metric is Einstein, okay, in this particular case we are looking at the Schwarzschild metric which is Einstein, okay, then the Lichnerovich acting on the transverse traceless piece gives you something which is again transverse traceless. Okay. So this tells you that the flow of the transverse traceless piece decouples from the flow of h and y. Okay, now we need to worry about this flow, but this problem is still computationally difficult. And here again we use a result which was used in classical perturbation theory in cosmology by Kodama and Sasaki. The result says it's not at all a trivial result, it's very painstaking, involves several pages, but what it says is that if you have any covariant second order differential equation, like the one we had, like the one we have here on such a space-time, this can be decomposed into pieces where the perturbations are scalar, vector and tensor on the D sphere. Okay. So I have this arbitrary perturbation Hij but I can think of 3 such perturbations, one which is a scalar on the D sphere, one part which is vector and one which is tensor. So I mean by tensor on the D sphere, I mean that when I do a coordinate transformation on the D sphere, it should behave like a tensor. Okay. So it should be given in terms of the tensor spherical harmonics, for example. So the Kodama and Sasaki found that you can always break up the problem into these 3 pieces. And we will start with the simplest of those, which are the tensor perturbations. Okay. So these transform as tensors of rank 2 on the D sphere when you do coordinate transformations on the D sphere. And how are they given? Well, they're given by these equations. In addition to all the other constraints on H, it's already transverse traceless, but it also has to obey HRA is equal to HTA equals 0, where A is any space-time index. Okay. So R and T are the special coordinates in the Schwarzschild metric. Okay, so now that we've already assumed that, and then we have the following ansatz for H. It's got some radial dependence, it's got a tau dependence which is of this form. Okay, so if omega is positive, then it's a growing mode. And we have a dependence on the angular coordinates on the D sphere, which are given in terms of the tensor spherical harmonics on the D sphere. Okay. So what we want is we want to look for solutions Hij which have omega positive, that means they are growing, and they should also be normalizable. And we are looking for such solutions. These would be unstable modes. So we can plug this back into the equation. We can plug this ansatz back into the equation, and what we get is the result that there are no unstable modes if the eigenvalue of this Lichnerovich Laplacian on the D sphere satisfies some inequality. Okay. And we already know a lot about the Lichnerovich Laplacian on the D sphere because it's just Laplacian, ordinary Laplacian plus some extra pieces. So we know what's the spectrum of the ordinary Laplacian acting on these transverse traceless tensors. Okay, so that's given by this, and staring at these two results, you can figure out that this inequality is always satisfied, and therefore there are no unstable modes. Okay, once you have made all these specialized approximations, you have a transverse traceless tensor, which is transverse traceless perturbation, which is like a tensor, two tensor on the D sphere. It does not lead to any instability. Okay, so so far so good. We've taken a specific ansatz and we have tried to prove some stability results. But the question that we want to ask is, how general is the ansatz? Okay. And why do we want to ask this question? So let's recall the kind of ansatz we took. Whether it's the trace or the transverse traceless part, we separated out the radial part, we separated out the angular part, which is quite natural. It's given in terms of some spherical harmonics. And we had a tau dependence of this particular type. Okay. And then we concluded that there were no normalizable modes with omega bigger than 0. But this is the same as the eigenvalue problem for the operator, for the Lichnerovich Laplacian. But there's a problem with this argument, and the problem is that generically operators like the Laplacian or the Lichnerovich Laplacian have a spectrum with a continuous part when you are on a non-compact manifold. Okay. So they don't always have just a discrete spectrum, and the corresponding eigentensors would be non-normalizable. Okay. So this is quite generic. Okay. But we could still have perturbations of compact support which are constructed from these non-normalizable modes, almost like a wave packet. We can still have something like that would grow in tau. Okay. So this ansatz is not very general. We should still argue that there are no perturbations that grow in tau. And although this is a technical point, this point was also tackled in the classical stability calculations in relativity, where a proof was given by Wald for the fact that perturbations of the Schwarzschild metric do not grow in tau. And there's a very nice discussion of that in Chandrasekhar's book. So what we're asking is the analog of that for this particular calculation. Okay, so I have this perturbation. I don't want to assume a dependence on tau like I did before, but I can still separate out, I'm sorry, I missed the tensor indices here again. I can still separate out the R and the tau part and the spherical harmonic part. So I can think of the angular dependence as being given in terms of the spherical harmonics. There's no loss of generality in that. Sorry, this should have been alpha beta. So I can still do this, and I have a part phi which depends both on R and tau. And it's possible to show a more rigorous argument. So the rigorous argument that we actually show is that the integral of the norm of phi square and the norm of the derivative of phi square are both bounded under the flow from above by constants. Okay. So once you have these two integrals, these are like energy integrals in relativity for people who are familiar with the stability calculations. So once you have these two integrals are bounded, you can also derive an inequality where the norm of phi square is bounded by these two integrals from above. Okay. So this tells you that there's a pointwise bound on the perturbation over tau. Okay. So this means that there are no growing perturbations. This is the complete rigorous result, and this is analogous to the proof of Wald. Okay, so let me summarize what we have shown. So for the Schwarzschild spacetime and its higher dimensional analogs, we showed that there was no instability under the flow of the trace for any arbitrary static perturbation. So when we looked at the flow of the trace, we did not really restrict to anything. So there was no instability. And when we have transverse traceless perturbations which are static and which obey some special conditions, so these actually transform as rank 2 tensors on the D sphere, again we have no instability. And this analysis can actually be generalized easily to anti-de Sitter Schwarzschild black holes. Okay. So this can also be viewed, as I said, as a quantum stability result for these black holes in the Euclidean path integral approach to quantum gravity. It's closely related, computationally at least, to this off-shell stability notion of string theory. So I want to spend some time talking about some work that I hope to do for the future. So clearly the Gross-Perry-Yaffe unstable mode, which was found for the Schwarzschild black hole, is not in the class of perturbations we have studied. So we would like to widen our stability analysis, and we would like to consider perturbations which are scalar and vector as well on the D sphere. So the question is, what is that mode really? I mean, can we actually classify what type of perturbation it is? And another question that you want to ask is, are there any more unstable modes? How many unstable modes are there for all these Schwarzschild and its higher dimensional analogs? Okay. So there are arguments that suggest that the Gross-Perry-Yaffe type mode exists for all higher dimensional Schwarzschild black holes as well. It's not a rigorous calculation, but it's an argument. But what we really want to know is that the only type of mode? Are there other modes? And can we obtain an understanding of all the possible instabilities of these black holes, at least in the semi-classical approximation to quantum gravity? And finally, this problem of stability of non-compact geometries under that partial differential equation, which I call the Ricci flow, is of interest in mathematics as well. In fact, it's a subject in which a lot of people in maths are doing research on now. And in mathematics, a lot of techniques have been developed to calculate stability, to prove stability of manifolds, prove stability of compact manifolds, but none of those techniques are useful in such problems. So it turns out that the classical stability calculations of the kind done by many people, including Chandrasekhar, are more useful for this problem and might give more insights into stability of non-compact geometries under Ricci flow. I think I'll stop here. Yeah.
Thank you for the discussion. Wait, take the mic.
So you said that it can be extended to radius.
Yeah.
This is the high dimension.
Yeah.
And I think there is a problem with them. If you have the high dimension, there is a odd and an even vector mode. That is Kodama Ishibashi's calculation. So I think the odd mode cannot be computed exactly. So I don't know.
So I haven't done all the modes. Again, whatever I have done is only for those perturbations which are tensor on the D sphere.
So what kind of boundary condition did you use for ADS?
For ADS, again, I used Dirichlet or Neumann. Yeah.
This question is slightly different from your talk, but it has been triggered by naked singularity discussions.
Right.
If I change remove the horizon, you started with 1 minus alpha over r to some power, change the sign of that alpha, then I don't have horizon, but I will get classically naked singularity.
Right.
Can you possibly extend this analysis to check what happens?
I haven't thought about that. In fact, I asked Pankaj the same question about this. So I'll think about it and tell you. It's not something obvious.
Yeah.
This is related to some of the things which I have been doing recently. So you have applied on a manifold with boundary, Dirichlet or Neumann boundary conditions. There is no dimensional parameter which is introduced by the boundary condition itself. Okay. Now you are essentially looking for bound states possible for something like a Laplacian operator on a manifold with boundary. And if we introduce a mixed boundary condition, like Dirichlet plus epsilon times Neumann, because epsilon is required to bring out the dimensional thing. Then it introduces a dimensional parameter, which will characterize how much is the width of the bound state itself.
Okay, computationally, when I did Dirichlet plus epsilon times Neumann, I did not get any difference in my results, stability results. Okay, so I mean, of course, the differential equation problem will become different when there are different boundary conditions. But finally, you want the conclusion, you know, that these black holes are stable. There's no change to the conclusion. That's why I didn't really give much emphasis to the boundary conditions.
Because if I don't take this black hole metric, if I take simply ordinary R2 or R3 with the boundary hole, and there in the normal case there are no bound states.
Yeah.
But with this thing there are new bound states, which go like e to the power minus epsilon times r, where that epsilon is the dimensional parameter. So that will introduce certain new instabilities of the negative eigenvalues which can arise.
Okay, it doesn't arise in my problem, but I can show you the details later.
I actually have two questions. The first one is the string theory motivation which led to the Ricci Flow equation.
Right.
I'm sure you know that, you know, if you go to the next order in sigma model perturbation theory, you have higher order terms.
Yeah.
Have you considered those?
Yeah, it doesn't make sense. First of all, I don't think the taking the second order makes sense at all. Because when you go to a regime in which you say the first and second order are both important, in that regime all orders become important. So it is a non-perturbative regime. Makes no sense to truncate to just second order. And if you do truncate, it turns out that the differential equation is ill-posed. So it already tells you that there's a problem.
The other question I have is something you mentioned about Lorentzian geometries and flow in such geometries. You of course work in Euclidean space.
I work in Euclidean space because of that.
Yes, and then you eventually, to make statements about stability of Lorentzian geometries, you wish to make a Wick rotation.
Yeah, but the statement about stability is only in the path integral approach, the Euclidean path integral approach.
So will you be making any statements at all about Lorentzian geometries?
No, I don't think you can. I don't think you can in string theory also, because although they don't really emphasize the point, that flow equation was derived after Wick rotation.
I have two questions.
Yeah.
One is that even if you go to Euclidean regime, the metric looks 1 minus 2m over r dt square plus. So there is no reason to put a boundary at r equal to 2m. You can go up to the origin. There is no reason.
No. Once you Wick rotate, your Wick rotated metric is only in the region from horizon to infinity, right?
But if I
and then you have a singularity if you don't actually change the period of the time. The time becomes periodic with a period which is appropriately chosen so that you have no singularity.
But if I write the there is a path integral approach I can follow. But otherwise, if I just write the metric 1 minus 2m over r dt square plus a, there's a well-defined metric, but singular at the origin. And I can write the Laplacian. Then I can ask, I mean, because you never use the path integral, then I have trouble because that Laplacian operator is not self-adjoint operator at the origin.
That's related to the problem of the Ricci flow not being well defined on Lorentzian space.
So
that's why I don't do it.
Down.
Yeah. So
you agree with that?
I'm sorry?
So analysis breaks down because
no. The Ricci flow, I'm taking the Ricci flow only through static spacetimes for that particular reason.
But I am also considering static spacetime. But okay, we'll discuss.
Yeah, we can discuss.
Second question is, even if you put a cutoff at r equal to 2m, there are infinitely many possible boundary conditions, which for all of which this del square is a self-adjoint operator.
Sure.
So you have to consider all of them even to assert stability in this calculation.
I don't understand why. I can talk to you later about the calculation.
Specialized perturbation. Even in your context, it is a very specialized perturbation.
Okay, so it is natural for what perturbation I put is up to me. So it's very natural for me to take something of compact support, which is 0 at both the ends.
I don't mean that way. The Laplacian operator, you put boundary conditions Dirichlet or Neumann. I am saying that these are very, very specialized. You already said about mixed. In fact, there are infinitely many such things at the boundary.
Okay.
They are all natural from the context of this activity.
Yeah, so we can talk about what boundary conditions you mean later. and I can tell you if the analysis will change or not, because it won't change for a combination of Dirichlet and Neumann.
I know, but there are
Try time.
infinitely many of them. And physics, I don't know what is. The physics, because this case is, as you know, quasi-normal mode, things going in. But here,
no, I think it's a very well-defined ODE where I can put boundary conditions where both the perturbation, at both ends the perturbations go to 0. I can show you what differential equation I have.
I am not objective, but why do you choose these?
No, there is, what I am trying to say is that I want to think of the perturbation as being of compact support. Okay, so I say that the perturbation goes to 0.
Then the boundary conditions will determine what combination you are going
No, which eigenmodes of which differential operator?
It's only a wave packet. Your perturbation is a wave packet.
Yes.
You want to expand it in modes of the Laplacian operator. Which has some specific
No, I'm only assuming the expansion in terms of the Laplacian, the spherical harmonics. So I'm assuming a special ansatz for the perturbation based on, so the perturbation has some part which is radial dependent, tau dependent, and angular coordinate dependent. The angular coordinate dependence is given by the spherical harmonics. It's a very general.
Now getting a little technical, so maybe you should do this in on this issue, or something else, then we'll go in order.
I want to make a comparison with your calculation of what I know with Yang-Mills case, where you do the effective action calculation, and you know that if you perturb the thing, it's unstable. Physics is very well understood over there. Okay, it's something surprising over there, and the instability also essentially is restored because you take the quadratic terms and so on.
Right.
That's another issue. Now, similarly, in the Einstein action here, if you do a perturbation about any solution here, are there instability is known? Do you make what I mean is that is quantum gravity unstable in the same way as the Yang-Mills theory is?
Okay, nobody knows the answer to that. Okay, so Gross-Perry and Yaffe, for example, have some possible list of processes which happen when there is this instability, but I don't think anything is known. I think we are at the stage where we're still trying to classify all the unstable modes, try to understand the nature of the unstable modes, see if there is, for example, is there only that Gross-Perry-Yaffe type mode? Okay, if there's only that instability, we concentrate on that. Is there something more? We are still at the stage where we're trying to answer that.
Actually, on this same point,
Yeah.
I think you said that there is this instability discovered by Gross-Perry-Yaffe, but you don't know what it is?
No.
Or,
You don't know if there is more.
No, that's true, but what is this mode? I mean,
So this is
what's the physics?
Okay, this is a negative eigenvalue of that Lichnerovich
Sure.
Laplacian. So all that you know is that in the path integral approach, it makes the action, it decreases the action. That's all you know.
No, I understand the mathematical result.
Yeah.
But anytime you have an unstable mode, you can calculate the eigenfunction.
Okay, you can't calculate the eigenfunction.
Well, why not?
What these people did was a numerical result where they found that it is unstable. It's not, you can't calculate that.
Was there a question there?
Just a slight confusion. When you do the quick rotation,
Yeah.
don't you get a conical singularity?
Yeah, you can remove the conical singularity by putting the appropriate period for the time.
I see.
You do all that. So I'm assuming that you do all that.
No, there's a load that the Euclidean action of Euclidean quantum gravity is not bounded below, and the reason is some conformal factors.
Okay.
At some point, you should be seeing that in this.
So so in the Gross-Perry-Yaffe calculation, they sort of do a procedure which removes the conformal factor, because the conformal factor, at least in perturbative quantum gravity, is supposed to be gauge. That is the belief. So this is not the conformal instability. So this is an instability which is different from that.
Yeah, but that is also there. And
that is also there. That is also there. That's.
So, any other questions? What about people in the back? Okay, awesome. Very front.
See, this is about this Ricci Flow and Poincare conjecture. I was very impressed by the person not accepting
Yeah.
this medal and so on.
Right.
So I went and read his paper.
Right.
I didn't understand anything.
Right.
But however, he uses this Ricci Flow.
No, the mathematicians also don't understand much.
And then he uses ideas of entropy and so on.
Right.
So I wonder whether you understand it.
No, actually, it's a crazily written paper, and even the mathematicians had a lot of trouble trying to figure out where the mathematics comes in, because he has all these ideas which are motivated by a partition function and a integral over configurations with some measure. So it looks like a statistical mechanics partition function, and I believe that some of the proofs that he got, so something which he uses crucially in the proof comes as a natural functional in string theory. So it is also possible that the idea struck him when he went to a workshop on string theory for mathematicians at Princeton. So I mean, if you read the paper, it looks like he's interested in physics, does not know much, but has borrowed ideas from it.
Is there any mathematician or physicist in India who understands this?
No, I don't think people really understand that section on the partition function. I looked through it myself when I was reading his paper, but...
So maybe you can teach mathematicians that part.
Well, I don't know what its relevance is for the rest of the paper. It just exists by itself. It's a construction. I don't know what its relevance is for the proof of the Poincare conjecture.
Thank
you. Okay, so I think we can probably close at this point, and we will come back at 4 p.m. for